Hi viewers, welcome to the online series of lectures on the course of Introduction to Category Theory. So I have written down the basics related to the teaching of this course on the board. You can see from here that there are two titles for this course, Introduction to Category Theory or Abstract Algebra, depending on the course codes, CAC 490 or Math T11. The textbook that we'll be following for this course is written by David I. Spivak from MIT. The title for the textbook being Category Theory for Scientists. The textbook is freely downloadable from internet using this link. About the prerequisite for the course. It is quite natural to have the prerequisite of basic abstract algebra to learn category theory, since category theory is an advanced abstract algebra course. But I am relaxing the requirement following David I. Spivak, since most of you don't have exposure to the abstract algebra. So for me, the prerequisite for the course would be basically basic linear algebra or elementary linear algebra, along with mathematical common sense. So what I mean by mathematical common sense will be clear throughout the first lecture. Okay, so what do we want to do in the first lecture? I will discuss very briefly on the main idea of category theory. Before we formally start the course, I give you a flavor of what category theory wants to achieve in general mathematical setup. Let me be a little more precise about what I mean by general mathematical setup. So, category theory is about translating all mathematical ideas related to stuff like set, group, monoids. If you are not familiar with these terminologies, don't be scared. I will explain them in the first lecture. Today's lecture. Vector spaces. You all know what a vector space is from linear algebra. Group representations, etc. Group representations, etc. So these are the mathematical stuffs I mean by all mathematical ideas, and we want to translate the ideas related to these mathematical stuffs into a universal language, so that the constituent stuffs here talk to each other. Okay, so these are the old mathematical ideas that we are familiar with. We want to translate these ideas into a different language, which we call a universal language of category theory, under which the constituent stuffs will start talking to each other. So the goal of this first lecture would be to give you a flavor how this happens. So here you can see different terms. So I assume that you are not familiar with them. Some of you might be familiar with these ideas, but that's an exception. I consider that as an exception. So I will explain what it means by a group first, and then I will give you the basic definition of a category and try to understand how can we construct a group, construct a category out of a group. Okay. A group denoted by G is a non-empty set together with a distinguished element one in G called the neutral element or unit. By the way, there is one other thing that I want to tell. If you don't understand the tiny details of the first lecture, don't feel upset for that, because I don't want you to understand the fine details of the first lecture. I want you to see the big picture. So as long as you can see the big picture, you are okay with the first lecture. Okay? All right. Secondly, a binary operation from G cross G to G, called multiplication is given. Called multiplication it means that if you have a pair of two elements from this set, it will give another element G dot H in G again. Okay? That is again in G. Thirdly, for each element G in this set G, there exists a unique element G inverse in G called the inverse. Okay? Such that the following properties are satisfied. Let me write down those properties. The first property being unitality. Unitality which states that for all G in the set G, the set big G, the multiplications, there are two multiplications. One is 1 dot G, another one is G dot 1. They have to be the same, and they are both equal to the element G itself. The second property is called associativity, which states that for three elements G, H, and I in the set, one must have G dot H dot I as the same as G dot H dot I. It means that you do the group multiplication of H dot I first, following the group multiplication with G. You will get the same result if you first multiply G dot H and then multiply the resulting group element with I. Okay? They will give you the same group element at the end. 3. Inverse law. It tells you that for all the group elements in the group, the multiplication of G with G inverse is the same as the multiplication of G inverse with G, and that is precisely equal to the neutral element of the group. Okay, so this is the definition of an abstract group. At this stage, we need the definition of a category. So let me write down the definition of a category. Definition of a category. A category consists of a collection calligraphic C0. I will denote the category by calligraphic C. So C consists of a collection C0 whose elements are called the objects of calligraphic C. We will usually denote the objects of C by uppercase letters. We'll denote the objects by the uppercase letters X, Y, Z, and so on. Okay. Secondly, we have a collection denoted by calligraphic C1 whose elements are called morphisms or arrows. Of the category C, which the arrows will be denoted in the lecture by the morphisms will be denoted by lowercase letters like F, G, H, and so on. Okay, so a category C consists of these two collections. One collection is called the collection of objects, and the other collection is called the collection of morphisms. So how do these two connections talk to each other? We'll now explain that. So we have these two collections. One is called the collection of objects and the other one is called the collection of arrows or morphisms, such that each morphism assigns two objects called source and target. So in the literature, you will find different names for the source and target. The source is also called domain in the literature, and the target is called codomain. So, for example, given an element F in the collection of morphisms, we call the source of F, we denote the source of F with SF and the target of F with TF. Say the source of F is an object X which is in the collection C0, so is the target of F denoted by Y. We can draw it diagrammatically using this diagram. Okay. So F is an arrow which takes object X to object Y. So far so good. Now, we also need for each object X in this collection of objects C0, each object X in C0 has a distinguished morphism, called the identity morphism on the object X from the object to itself. Okay? Then, for each pair of morphisms, F and G in C1 such that target of F is the same as the source of G so let me draw a diagram explaining the situation here. We have three objects here connected by two morphisms. We demand the source of G, meaning this object Y, to be the same as the target of F here. Okay. So if you have this situation here, these two morphisms are given like this. One must have a morphism which is the composition of these two morphisms, F and G, which we denote by G after F. It is a morphism which takes the object x to z. As you can see from this diagram, that G after F takes the object x to z. Okay? Alright. Now these structures are required to satisfy the following axioms. Let me write down the axioms. These structures are required to satisfy the following axioms. What is the first axiom? The first axiom is that of unitality, which states that for every morphism f from x to y, the compositions given by F circle the identity morphism on X is equal to the identity morphism on Y composed with F. And they are both equal to F itself. Okay. So there is a small warning here. Which tells you that the identity morphism on X composed with F does not make sense. Why? Because diagrammatically you draw the morphism like this. The morphism F takes the object X to object Y. And this is the identity morphism on X. Diagrammatically, it is given this way. The morphism takes the object X to object Y, and the identity morphism on X is given by this loop. So, the identity morphism X composed of with F does not make sense, since F acting on the object will be finally in the object Y, but the identity morphism on X acts on X. Therefore, obviously, this cannot make sense. Alright? So does not F composed with identity morphism on Y. This is also not valid. Let us move to the associativity axiom. For category theory, for the definition of category. Associativity. So let me write down the morphisms corresponding to 4 objects this way. F is a morphism from X to Y. G is a morphism from Y to Z. And H is a morphism from Z to W. where we want to understand these morphisms. In order to understand it better, I try to draw a diagram. Okay. So now you see that you can go from object X to object W in two different paths. Let us first go from X to Z via morphism G composed with F, and then from Z to W via morphism H. So the final path is this one via this morphism and that morphism, resulting in the morphism H composed with G circle F. So this is a morphism from X to W. We can again go from X to W using a second path. Let me show this to you. We can first go from X to Y via morphism F, and then from Y to W using the morphism H composed with G. So first we go from X to Y via morphism F, and then from Y to W via morphism H composed with G. So the resulting morphism is precisely H circle G composed with F. So the associativity axiom demands that these two morphisms, the final morphisms, should be the same. H composed with G circle F should be the same as H circle G composed with F. This morphism also takes the object X to W. Alright, so this completes the definition of the category. Thank you very much for the first segment of the lecture. In the second segment, we'll address the question on how to make an abstract group a category.